Have you ever felt that just beneath what we call reality, there lies another layer of the world gently brushing against our everyday lives? In the quietest moments, there are times when we sense something unseen, close beside us, yet drifting softly beyond our sight. Tonight, we will open the door to that bold hypothesis where scientists believe another reality may be overlapping with our own, light as the shadow of a dream. If the thought of a second reality has ever made you pause and wonder what you are truly living inside, share your feelings in the comments. Do you believe something is quietly moving alongside this world, or is it all just an illusion of perception? I would love to hear your honest thoughts. So, is what we call reality truly complete? There are moments when the world grows quiet enough that you can feel the edges of reality soften, as if the universe is whispering that what we see is only the first page of a much larger story. In those still moments, the mind begins to ask questions it usually keeps folded away. Questions that rise slowly like breath on a cold morning. Gentle, inevitable. What if the three dimensions we move through each day, the familiar axes of up and down, left and right, forward and backward, are not the whole of existence at all? What if time itself, the river we believe flows in one single direction, is only a shadow cast by something deeper, something richer, something beyond the grasp of our intuition? These are not new questions, but they return to us now with renewed weight because modern physics keeps tugging at the edges of our certainty. As the physicist Brian Greene once said, our senses give us only a tiny slice of what is actually out there. And that idea, fragile yet powerful, becomes the thread that pulls the entire fabric of our understanding into a new shape. To ask whether reality has more dimensions is to ask whether we are living inside a simplified version of the truth. A truth trimmed down by biology and evolution for the sake of survival, not understanding. Our ancestors never needed to perceive higher dimensions to gather food, find shelter, or raise families. And so, as neuroscientist Donald Hoffman reminds us, evolution shapes perceptions to be useful, not to be accurate. Perhaps that is why our direct experience clashes so sharply with the equations that govern the world. The mathematics of general relativity tells us that space bends and stretches like a living fabric, while quantum mechanics insists that reality flickers with uncertainty at the smallest scales. These two visions are not gentle companions. They grind against each other like tectonic plates. And in the friction between them, scientists have found hints that the universe might be built from more layers than we can perceive. Einstein himself once wrote, "The most incomprehensible thing about the universe is that it is comprehensible." Yet even he suspected that our understanding was incomplete. For all his brilliance, he still believed that what we call space and time were only the beginning of a deeper geometry. And so we return to the question that lingers like a soft echo in the night. Are we truly seeing reality, or merely a cross-section of something vaster? Imagine a sheet of paper drifting through a three-dimensional room. A two-dimensional creature living on that sheet would never see the full shape of the world around it. It would know only lines and edges, never the depth that surrounds them. We are perhaps that creature, gliding unknowingly through a structure richer than our senses can hold. Theoretical. Physicist Nima Arkani Hamed once said, "Space and time are doomed." Not as a warning, but as an invitation to imagine more. He believes that the universe may not be built from space and time at all, but that these familiar concepts emerge from a deeper network of relationships, patterns, and symmetries living in dimensions beyond our sight. When you view the world this way, the conflict between intuition and physics begins to make sense. Our intuition evolved in the slow, predictable domain of everyday life. But the universe operates on scales of energy and time that stretch far beyond what our minds were built to grasp. It is no surprise that the cosmos feels strange. It is no surprise that the equations we write can see farther than our eyes. But perhaps the most poetic lesson in all this is that mystery is not a flaw in the human condition. It is one of our great treasures. The unknown is not a wall, but a window. And when we press our faces to the glass, we glimpse the shimmering outline of possibilities waiting to unfold. When physicists propose that multiple realities may be overlapping with our own, they are not indulging in fantasy. They are responding to the stubborn whispers of the equation's patterns that appear again and again across different fields. Whether in string theory, where additional dimensions are required for mathematical consistency, or in cosmology, where the behavior of dark matter and dark energy hints at hidden structures. The universe seems to be telling us that the map we carry is incomplete. Another reality overlapping ours, like a ghostly melody woven through a familiar song. What would that mean for us? Not necessarily parallel worlds filled with alternate selves, though that is one possibility. Instead, it might mean that the forces shaping our world are influenced by structures that lie just outside our perception, shaped by dimensions we have never walked through. In my own reflection, I find this idea neither frightening nor strange, but deeply comforting. It reminds me that the universe is grander than our brief lives suggest, that our questions matter, and that wonder is a form of participation in the cosmic story. To live with curiosity is to reach toward the unknown, the way a plant reaches towards sunlight. As I speak these words, you may feel a gentle widening inside your awareness, a small shift, as if the world around you has grown just a little larger. That is the gift of contemplating deeper realities. Not certainty, but possibility. And perhaps that is the lesson worth holding on to. Reality is not a fixed stage, but a living field of discovery. And every insight we gain becomes a lantern we carry into the dark, illuminating not only the world, but ourselves. If you feel a quiet spark of curiosity at this moment, a shimmer of wonder rising softly within you, I invite you to linger with it. Let it guide you deeper into the mysteries that scientists grapple with every day. Mysteries that remind us we are part of something vast, something ancient, something breathtakingly intricate. And if you found calm or inspiration in this journey through the folds of reality, I gently encourage you to like this video and subscribe, not as an obligation, but as a shared step on this path of exploration. Your presence here matters. Your curiosity shapes the very direction of this channel. We are travelers together, moving through a universe that is far richer than our senses reveal. And as long as the questions remain, the adventure continues. So perhaps the true question is not whether reality is complete, but whether we are ready to open our minds to what might be waiting just beyond the veil. Gravity has always been our quiet companion, a whisper of force that cradles oceans, shapes mountains, and keeps our feet pressed gently to earth. Yet, the moment you lift a small magnet and watch it pull a paperclip upward against the pull of an entire planet, something in the mind pauses, tilts, wonders. How can the delicate tug of a tiny object overpower the weight of Earth itself? How can the force that binds galaxies be defeated by something that fits in the palm of your hand? Physicist Richard Feynman once remarked that gravity is ridiculously weak. And even in his half-joking tone, you can hear the bewilderment of someone who spent a lifetime listening to the universe's deeper rhythms. Gravity is everywhere, shaping everything, yet it arrives like a feather instead of a hammer. This gentle paradox has become one of the great puzzles of modern physics. Some call it the hierarchy problem, a name that sounds clinical, almost bureaucratic, but beneath it lies a mystery of astonishing depth. Why is gravity so much weaker than the electromagnetic, strong, and weak nuclear forces? Why does it fall behind by a factor that strains the imagination? A number with 30 zeros trailing behind it. Nature rarely creates gaps that large without meaning something, whispering something, pointing toward a hidden layer folded just outside our sight. And so the mind wanders through the dark corridors of possibility, not with fear, but with curiosity. Could it be that gravity is not weak at all, but simply spread thin across a wider expanse of space than the other forces occupy? Could it be slipping gently through hidden dimensions, like water passing through cracks in stone? The idea may sound fantastical, yet it rises not from wild imagination but from equations that resist any other interpretation. As theoretical physicist Lisa Randall once said, "Sometimes the universe forces your hand, because the mathematics keeps pointing in a direction you did not expect." If gravity is leaking into hidden dimensions, its weakness here is not a flaw, but a clue. A sign that our familiar world of 3 spatial dimensions is only a thin slice of a much larger realm. Like shadows cast on a wall, we experience only the narrow projection of something richer, deeper, more layered than our senses can hold. In this gentle idea lies the seed of something more profound. Because if gravity alone can wander into those unseen spaces, then our universe may float like a delicate membrane suspended in a broader cosmic sea. And the forces we know electromagnetic, weak, strong, cling to this membrane, while gravity roams freely across the greater landscape. Einstein himself once wrote that the most incomprehensible thing about the universe is that it is comprehensible. And perhaps hidden dimensions are part of that curious truth. We understand the world so well only because we are allowed to see one small illuminated chamber, while the rest of the mansion sleeps in darkness. But the question deepens. Why can gravity not unite with the other forces in the standard model? Why does it stand apart, aloof, like an old god who no longer speaks the language of its younger siblings? The standard model is like a finely woven tapestry, each thread of particle and force interlocking in perfect tension, Electromagnetism dances with the photons. The strong force binds quarks into atomic hearts. The weak force touches the delicate process of nuclear decay. But gravity refuses to join the dance, refusing every attempt to weave it into the same mathematical fabric. Stephen Hawking once called gravity the odd one out, a force that does not obey the rules that govern its companions. And the more physicists try to merge it with quantum theory, the more it slips away like mist between fingers. This stubbornness has pushed science toward the edge of imagination, and at that edge awaits the possibility of extra dimensions. If gravity is free to wander through hidden realms, then maybe the reason it resists unification is simple. It was never wholly ours to unify. It does not live solely within our familiar three-dimensional space, and so the equations we use to describe particles confined to this space cannot hope to capture it fully. The picture becomes almost poetic, as though our universe is a quiet room in a vast house, and gravity is the only force aware that the hallway outside even exists. Experiments have pressed their ears to the walls of this room, listening for any sign that gravity behaves strangely at small distances. And though the walls remain mostly silent, the search continues. Because as physicist Nima Arkani Hamed said, when nature hides something this effectively, it is usually something worth finding. As the theories unfold, a quiet beauty emerges. The universe may not be a flat, simple canvas, but a layered composition, a symphony of spaces nested within spaces. And gravity, wandering gracefully across these layers, may be the thread that ties them all together. In the stillness of this thought, I find myself imagining gravity not as a force, but as a storyteller, carrying messages between worlds we cannot yet see. Perhaps its weakness is not weakness at all, but generosity distributed across realms beyond imagining. And there is a lesson in that, quiet but profound. Strength does not always roar, nor does importance demand volume. Sometimes the most essential forces in our lives are the ones we barely feel, the ones that move slowly, patiently, shaping everything without needing to declare themselves. Gravity, in its tender subtlety, becomes a metaphor for the truths we overlook. The quiet relationships that sustain us, the unnoticed moments that change us, the invisible bonds that hold our world together. As we drift through these ideas, there is a kind of comfort in realizing that the universe is deeper than we can see, richer than we can measure. It means we have not reached the limits of wonder, and that curiosity still has a long road ahead. And so I find myself grateful for mysteries like the hierarchy problem, because they remind us that the world is not finished revealing itself. If you have felt that quiet astonishment too, that sense of walking at the edge of a deeper reality, then gently press the like button. Subscribe if you feel called to keep wandering with us, and share your thoughts below. Your voice becomes part of this journey, another thread in the fabric we are all trying to understand. For now, let the question linger in the air like stardust. If gravity is so weak here, what worlds is it strong in elsewhere? There are moments in the history of science when the universe whispers instead of shouts, and those whispers become turning points that reshape everything we believe we know. The orbit of Mercury was one of those whispers, soft, persistent, impossible to ignore. For centuries, astronomers charted its path around the Sun, and yet the planet refused to obey the perfect clockwork predicted by Newton's laws. Its perihelion advanced a little too far, too steadily, as if pulled by a gravity no one could see. That tiny discrepancy was like a grain of sand caught in the gears of physics, small enough to overlook, yet large enough to trouble anyone who listened closely to nature's rhythms. Einstein was one of those listeners. And he once wrote, "The eternal mystery of the world is its comprehensibility." To him, Mercury's odd motion was not an irritation but an invitation to reimagine gravity not as a force, but as the bending of space and time themselves. When he unveiled general relativity in 1915, the new theory fit Mercury's orbit with a grace that felt like poetry. Suddenly, the small anomaly was revealed as a window into a deeper geometry of the universe. This story reminds me of a truth I've grown to believe deeply as both a scientist and a storyteller: that the universe often reveals its greatest secrets through its smallest irregularities. Like cracks of light, slipping through a door before it opens fully. And just as Mercury guided Einstein, light itself guided the birth of quantum mechanics through another strange whisper known as the ultraviolet catastrophe. At the beginning of the 20th century, physicists studied the spectrum of light emitted by heated objects. Classical physics predicted that at high frequencies the energy would climb toward infinity, a result so absurd it threatened to collapse the entire foundation of physics. Max Planck spoke of this moment with humility, saying, "I was forced to consider the energy as existing in discrete units." And with that step, that reluctant but brilliant step, quantum theory was born. What moves me about this era is not only the scientific revolution it ignited, but the mindset it required. It demanded that physicists abandon comfort and step into uncertainty, the same way we step into the darkness of a forest and trust our senses to adjust. In that sense, the ultraviolet catastrophe was not a disaster, but a gift. It showed that even our most trusted equations could unravel when confronted with the truth. And that humility is often the key that unlocks new dimensions of understanding. When I look at these two episodes in the history of science, Mercury's restless orbit and the runaway predictions of classical radiation, I see more than equations and experiments. I see reminders that the universe is not obligated to fit our expectations, but we are invited to expand our minds to match its depth. Steven Weinberg once said, "The more the universe seems comprehensible, the more it also seems pointless." And yet I've always felt the opposite. The more it reveals its inconsistencies, the more meaningful the quest becomes. Because every anomaly is a nudge, a tap on the shoulder, a whisper that says, "Look again." And it makes me wonder whether these anomalies are never accidents, but intentional invitations from the cosmos itself. Perhaps the universe speaks to us in misalignments, like a musician tuning an instrument and letting one discordant note reveal how far the harmony can stretch. If everything behaved perfectly, flawlessly, predictably, would we ever grow beyond the boundaries of what we already know is less than, BR is greater than? Consider how both relativity and quantum mechanics arose not from grand mysteries but from small imperfections. Einstein needed only a tiny misstep in Mercury's motion to reshape gravity. Planck needed only a broken curve of thermal light to reinvent the atom. What does that tell us about the nature of discovery? Is less than BR, is greater than. To me, it reveals that truth hides in the margins, in the places where the world refuses to behave, in the subtle tremors that disturb our certainty. Maybe that is why I've always been drawn to the quiet side of science, the meditative side, where you sit with a problem not as a puzzle to conquer but as a companion to understand. There is something profoundly human in the idea that our greatest breakthroughs come not from control, but from listening. And when we place these stories side by side, Mercury's orbit curved by spacetime and the quantum steps of light quanta, a larger reflection emerges. Both revelations taught us that reality is not smooth, not linear, not obedient to the human desire for simplicity. Instead, it is layered, textured, full of hidden geometry and sudden leaps. Richard Feynman captured this beautifully when he said, "I think I can safely say that nobody understands quantum mechanics." But he also meant it as praise, a tribute to the universe for remaining deeper than our expectations. As I reflect on these scientific crossroads, I also reflect on what they teach us personally. We all have moments when something in our lives refuses to fit the model we expect, when the path curves unexpectedly, or when the light does not behave the way it should. In those moments, perhaps the universe is inviting us to shift perspective, to reconsider our assumptions, to explore a deeper truth within ourselves. It's comforting to think that the same cosmos that bends Mercury's orbit and quantizes light also shapes our journeys, nudging us gently through disruptions, urging us toward greater clarity. And just as Einstein leaned into the anomaly rather than abandoning it, we too can lean into the unexplained corners of our lives to discover what new understanding awaits. This is why I love sharing these stories with you. Not to drown you in equations, but to remind you that our universe is a living poem, a cosmic meditation, a dance between certainty and mystery. And if these ideas stir something in you, some spark of curiosity, some quiet sense of wonder, I invite you to let it grow. Because when you stay curious, when you keep looking closer, you join a lineage of thinkers who refuse to accept easy answers. You walk the same path Einstein walked when he stared at Mercury's orbit, the same path Planck walked when he questioned the collapse of classical physics. You step into the tradition of those who believe that small mysteries lead to vast truths. And if you've enjoyed this journey through the soft edges of physics, through the quiet revolutions hidden in the sky and in the glow of heated metal, I hope you'll let your curiosity echo a little further by supporting this channel. A gentle like, a small subscription. It helps this space grow. And it tells the algorithm that there are still minds in the world who crave wonder and depth. As we drift toward the close of this meditation, I'm left thinking about one simple thread connecting every breakthrough we discussed. The universe does not reveal itself all at once. It opens slowly, like a flower unfolding at dawn. And in those delicate openings, in those tiny imperfections, lie the clues that reshape our entire understanding of reality. Maybe that is the greatest lesson of all, that in science, as in life, The small things are often the doorway to the infinite. There are moments in the long history of physics when a single idea arrives like a quiet ripple across the surface of the universe. Gentle at first, but destined to reshape how we understand reality itself. One of those ripples appeared in 1919, when Theodore Kaluza asked a question so simple that it felt almost childlike, yet so daring that it challenged the very geometry of existence. What would happen, he wondered, if Einstein's four-dimensional spacetime were given one more direction in which to breathe? It was not a reckless leap, but a soft intuition rooted in the desire to unify the world. Einstein had shown that gravity was the curvature of spacetime, a graceful bending of the cosmic fabric. Maxwell had revealed that electricity and magnetism were not two separate forces but two voices of the same symphony, intertwined like threads of light. And Kaluza felt a longing to bring these insights together, to let gravity and electromagnetism share a deeper origin. So he wrote down Einstein's equations again, but this time he allowed them to stretch into a fifth dimension. Not a dimension of fantasy, but a mathematical extension of space itself. And when he solved those equations, something extraordinary happened. Out of the geometry of that five-dimensional world emerged two sets of forces. One set described the familiar curvature that creates gravity, and the other reproduced the full structure of Maxwell's electromagnetic equations. It was as if nature had been waiting for someone to notice. As if two distant rivers of physics suddenly revealed themselves to be branches of the same hidden lake. Einstein himself wrote in a letter that Kaluza's idea made a deep impression on him. And decades later, the physicist Michio Kaku would reflect that higher dimensions are not speculation but a natural consequence of unifying the laws of nature. But Kaluza's triumph produced an unsettling puzzle. If a fifth dimension really existed, why could no one see it? Why did our senses, our telescopes, our experiments, all return the same verdict? That the universe appears resolutely four-dimensional? For a moment, the idea seemed to shimmer like a ghost. Brilliant, but impossible to touch. Until Oscar Klein arrived with a picture that was at once small enough to hide and elegant enough to understand. He suggested that the extra dimension was not stretched like the others, but curled tightly into a microscopic loop, so small that no human instrument could ever wander through it. Klein compared it to the surface of a drinking straw. From far away, the straw looks like a one-dimensional line. But up close, you discover that you can walk not only forward and backward, but also around its circular edge. That second path was always there, hidden in plain sight. And so a new way of seeing the universe emerged. A universe where some dimensions are vast, like the plains of night, and others are curled small like whispered secrets in the dark. As decades passed, Kaluza and Klein's idea drifted through the background of physics, overshadowed by the bright flood of quantum mechanics. But the seed they planted never died. When string theory appeared, it carried their legacy like a buried root, suddenly breaking the surface again. For in string theory, the equations refuse to work unless the universe has more dimensions than we see. 6 extra curled shapes need to exist, forming what we call Calabi-Yau manifolds, twisting and folding like cosmic origami. Each shape changes the vibrations of the strings, and those vibrations become the particles and forces of our world. Edward Whitton once said, "It's not that we want extra dimensions, it's that the mathematics forces them upon us." The deeper I reflect on that sentence, the more it feels like a lesson not only about physics, but about life. Sometimes the world asks us to look beyond what is comfortable, beyond what our senses insist is true. And that recognition brings a certain humility. For if dimensions can hide so perfectly, what else might exist just beyond the edge of perception? What other truths lie waiting in forms we have not yet learned to notice? As we drift slowly through this story, like travelers moving through a quiet corridor of starlight, a natural question rises. Why does geometry know so much about the forces of nature? Why should bending in one dimension produce light, and bending in another produce gravity? Einstein himself once whispered that the harmony of natural law reveals an intelligence of such superiority that it leaves us humbled. And perhaps that harmony is clearest in the way dimensions shape the world. Not by existing separately, but by weaving together in secret patterns of structure and symmetry. When I think of Kaluza again, sitting at his desk more than a century ago, deciding to place a single new coordinate into the universe, I imagine it like the stroke of a painter's brush across the night sky. A gentle line that reveals a landscape that was always there, waiting to be seen. And yet, the mystery remains. We cannot walk into the fifth dimension, cannot stretch our hands into that curled geometry, cannot witness directly the loop that Klein imagined. But we can feel the implications through mathematics, through symmetry, through the quiet correspondence between gravity and light. There is a kind of poetry in that, a reminder that truth does not always arrive dressed in visibility. Sometimes it stands behind the curtain, shaping the world from the shadows. As we move gently from one thought to another, like drifting between tides, I cannot help but offer my own reflection, that perhaps the universe is urging us to soften our certainty, to welcome possibilities we cannot yet touch. Whether or not extra dimensions exist as Kaluza imagined, the boldness of the idea teaches us something precious. Curiosity is the doorway to understanding, and humility is the light that guides us through. And if you've traveled with me through this quiet exploration, letting the ideas settle gently like dust across a beam of morning light, I hope you'll consider supporting this journey by liking the video and subscribing, not out of obligation, but because each gesture helps keep this shared space of wonder alive. As we continue deeper into the mysteries of higher dimensions, let us hold on to the thought that even the smallest addition to our understanding, a single new coordinate, a single new perspective can unfold the universe in ways we never expected. And perhaps, one day, when our tools sharpen and our minds grow still enough to hear the faint geometry beneath existence, we will discover whether the fifth dimension is merely mathematics, or whether it is a real and hidden path woven softly through the fabric of our world. There are moments in the long history of physics when a single idea arrives like a quiet ripple across the surface of the universe. Gentle at first, but destined to reshape how we understand reality itself. One of those ripples appeared in 1919 when Theodore Kaluza asked a question so simple that it felt almost childlike. yet so daring that it challenged the very geometry of existence. What would happen? He wondered. If Einstein's four-dimensional spacetime were given one more direction in which to breathe. It was not a reckless leap, but a soft intuition rooted in the desire to unify the world. Einstein had shown that gravity was the curvature of spacetime, a graceful bending of the cosmic fabric. Maxwell had revealed that electricity and magnetism were not two separate forces but two voices of the same symphony, intertwined like threads of light. And Kaluza felt a longing to bring these insights together, to let gravity and electromagnetism share a deeper origin. So he wrote down Einstein's equations again, but this time he allowed them to stretch into a fifth dimension. Not a dimension of fantasy, but a mathematical extension of space itself. And when he solved those equations, something extraordinary happened. Out of the geometry of that five-dimensional world emerged two sets of forces. One set described the familiar curvature that creates gravity, and the other reproduced the full structure of Maxwell's electromagnetic equations. It was as if nature had been waiting for someone to notice. As if two distant rivers of physics suddenly revealed themselves to be branches of the same hidden lake. Einstein himself wrote in a letter that Kaluza's idea made a deep impression on him. And decades later, the physicist Michio Kaku would reflect that higher dimensions are not speculation, but a natural consequence of unifying the laws of nature. But Kaluza's triumph produced an unsettling puzzle. If a fifth dimension really existed, why could no one see it? Why did our senses, our telescopes, our experiments, all return the same verdict? That the universe appears resolutely four-dimensional? For a moment, the idea seemed to shimmer like a ghost. Brilliant but impossible to touch. Until Oscar Klein arrived with a picture that was at once small enough to hide and elegant enough to understand. He suggested that the extra dimension was not stretched like the others, but curled tightly into a microscopic loop, so small that no human instrument could ever wander through it. Klein compared it to the surface of a drinking straw. From far away, the straw looks like a one-dimensional line. But up close, you discover that you can walk not only forward and backward, but also around its circular edge. That second path was always there, hidden in plain sight. And so a new way of seeing the universe emerged. A universe where some dimensions are vast, like the plains of night, and others are curled small like whispered secrets in the dark. As decades passed, Kaluza and Klein's idea drifted through the background of physics, overshadowed by the bright flood of quantum mechanics. But the seed they planted never died. When string theory appeared, it carried their legacy like a buried root suddenly breaking the surface again. For in string theory, the equations refuse to work unless the universe has more dimensions than we see. 6 extra curled shapes need to exist, forming what we call Calabi-Yau manifolds, twisting and folding like cosmic origami. Each shape changes the vibrations of the strings, and those vibrations become the particles and forces of our world. Edward Witten once said, "It's not that we want extra dimensions, it's that the mathematics forces them upon us." The deeper I reflect on that sentence, the more it feels like a lesson not only about physics but about life. Sometimes the world asks us to look beyond what is comfortable, beyond what our senses insist is true. And that recognition brings a certain humility. For if dimensions can hide so perfectly, what else might exist just beyond the edge of perception? What other truths lie waiting in forms we have not yet learned to notice? As we drift slowly through this story, like travelers moving through a quiet corridor of starlight, a natural question rises. Why does geometry know so much about the forces of nature? Why should bending in one dimension produce light, and bending in another produce gravity? Einstein himself once whispered that the harmony of natural law reveals an intelligence of such superiority that it leaves us humbled. And perhaps that harmony is clearest in the way dimensions shape the world. Not by existing separately, but by weaving together in secret patterns of structure and symmetry. When I think of Kaluza again, sitting at his desk more than a century ago, deciding to place a single new coordinate into the universe, I imagine it like the stroke of a painter's brush across the night sky. A gentle line that reveals a landscape that was always there, waiting to be seen. And yet, the mystery remains. We cannot walk into the fifth dimension, cannot stretch our hands into that curled geometry, cannot witness directly the loop that Klein imagined. But we can feel the implications through mathematics, through symmetry, through the quiet correspondence between gravity and light. There is a kind of poetry in that, a reminder that truth does not always arrive dressed in visibility. Sometimes it stands behind the curtain, shaping the world from the shadows. As we move gently from one thought to another, like drifting between tides, I cannot help but offer my own reflection, that perhaps the universe is urging us to soften our certainty, to welcome possibilities we cannot yet touch. Whether or not extra dimensions exist as Kaluza imagined, the boldness of the idea teaches us something precious. Curiosity is the doorway to understanding, and humility is the light that guides us through. And if you've traveled with me through this quiet exploration, letting the ideas settle gently like dust across a beam of morning light, I hope you'll consider supporting this journey by liking the video and subscribing, not out of obligation, but because each gesture helps keep this shared space of wonder alive. As we continue deeper into the mysteries of higher dimensions, let us hold on to the thought that even the smallest addition to our understanding, a single new coordinate, a single new perspective, can unfold the universe in ways we never expected. And perhaps, one day, when our tools sharpen and our minds grow still enough to hear the faint geometry beneath existence, we will discover whether the fifth dimension is merely mathematics, or whether it is a real and hidden path woven softly through the fabric of our world. For more than a century, physics has been gently whispering that the picture of reality drawn by our intuition may be too flat, too narrow, too bound to the comforting simplicity of particles as infinitesimal points drifting through an empty stage. When the early quantum pioneers tried to treat matter as little dots with no size and no structure, the mathematics trembled as if refusing a language too crude to express the truth. Energies rose to infinity, equations collapsed under their own weight, and nature seemed to push back with the quiet insistence of something deeper. As Richard Feynman once remarked, point particles make the infinities too hard to sweep under the rug. It was here that the idea of strings, slender loops of vibration, entered like a soft chord, resolving a long dissonance. Instead of treating particles as dimensionless specks, string theory gave them length, tension, and voice. A point is silent, but a string sings. And in that music, the infinities vanish. Not through invention, but through the mathematics gently aligning itself with the rhythms of something real. What startled physicists was not that strings worked, but that strings demanded more room to exist. They refused to vibrate consistently in the narrow corridor of three spatial dimensions, breaking into contradictions whenever the universe was assumed to be too small. When allowed to stretch through 10 dimensions, or in an even grander version, 11, the equations settled like dust on a still morning. Edward Witten once said, "String theory is not just a set of equations, it's the mathematics telling us what reality prefers to be." That sentence has lingered in my mind for years, because it captures a truth scientists rarely admit aloud. Sometimes the universe teaches us by refusing our assumptions. Why does string theory need 10 or 11 dimensions? Because the vibrations of a string are like the harmonics of a violin, and the violin must have space inside it to resonate. If the universe has too few dimensions, the notes clash, symmetries break, and the entire structure collapses. With 10 or 11, a breathtaking coherence appears. Forces that seemed incompatible: gravity, electromagnetism, nuclear interactions begin to speak the same language. To me, this is one of the quiet miracles of physics. When a theory is beautiful enough, it stops being just a human invention and starts feeling like a window into the world's original architecture. But if there are extra dimensions, where are they? Why can't we see them drifting around us like hidden layers of air? The answer arrived with another poetic idea: compactification. The dimensions may be small, curled tightly into shapes far tinier than atoms. And these shapes are not simple circles or tubes, but intricate geometries known as Calabi-Yau manifolds. A Calabi-Yau space is not something the mind grasps easily. It is a multi-dimensional sculpture, folded in ways our senses cannot picture, yet defined by equations so elegant that physicists felt as if they were discovering ancient carvings hidden beneath layers of abstraction. Each Calabi-Yau shape acts like the internal architecture of a musical instrument, altering the possible harmonics of vibrating strings. And here lies the next revelation: change the shape, and you change the laws of physics. Not metaphorically, literally. A universe with one Calabi-Yau geometry might have electrons of a certain mass, forces of particular strengths, and particles arranged into families like constellations. Another geometry might give rise to a world with entirely different chemistry, different stars, or no life at all. It is here that string theory quietly brushes against the idea of the multiverse. Not because anyone set out to imagine countless worlds, but because the mathematics refuses to pick a single geometry. Leonard Susskind once said, "The multiverse is not an idea we wanted, it is the idea that would not go away." And there is a humility in that admission. A reminder that nature may be far less concerned with our comfort than with her own internal consistency. As I read more about these geometries, I sometimes imagine the universe as a forest of invisible cathedrals, Each kalabiyao shape a silent sanctuary where strings vibrate in patterns that determine all of physics. And when cosmologists say that perhaps our universe is only one cathedral among countless others, I feel a strange mixture of awe and humility. If every possible geometry exists somewhere, then reality is not a single story, but a library. And our universe is merely one book whose pages we are just beginning to turn. Yet even as these theories grow grander, the heart of the mystery remains tender and human. Why does mathematics know more about the world than we do? Why does it predict dimensions we cannot see, structures we cannot touch, realms that might be as real as our own but forever hidden? Max Tegmark once said, "We discover mathematical truths not because we invent them, but because we uncover what reality has written." As a scientist, I cannot help but feel the weight of that sentence. When I sit alone at night, the thought that the world may be woven from vibrations in unseen dimensions fills me with a sense of quiet wonder. The universe, viewed through this lens, becomes less like a machine and more like a poem, one written in a language we are slowly learning to recite. And in that poem, there is a lesson that I return to again and again. The closer we look at reality, the more it slips through our fingers, revealing that certainty is not the goal of science, but curiosity. Perhaps that is the deeper power of string theory, not that it claims to be the final truth, but that it reminds us how vast the unknown truly is. As I reflect on this journey, I find myself thinking of all the explorers who stared at maps with great areas left blank, not with fear, but with anticipation. Our maps of reality still carry immense blank regions, labeled only by the softest speculations. Yet those blanks are the invitation that keeps the human spirit awake. If these hidden dimensions exist, they have been here all along, folded into every second of our lives, brushing our world with the quiet presence of a deeper architecture we have only begun to imagine. And if you felt even a flicker of wonder while traveling through these ideas, I invite you gently to leave a like and subscribe, not for numbers, but so this shared curiosity can continue drifting between us like a soft current in a vast ocean of thought. For in the end, physics is not only about equations, but about companionship on the long road toward understanding. And perhaps, somewhere in the echo of vibrating strings, in spaces we cannot see, our questions are already touching the edges of answers, waiting patiently in the dark. In the quiet hours when the world softens and the mind drifts like a small boat on a starlit tide, there is a thought that returns again and again, a whisper almost too delicate to name. What if the universe we know is only a surface? A thin, luminous film floating upon a deeper sea of dimensions we cannot touch. In modern physics, this idea has a name often spoken reverently by theorists who chase the hidden architecture of reality. They call it the brain, a three-dimensional membrane on which all the particles and forces we know are confined, except one: gravity. The idea is simple but carries the weight of a cosmic poem. Our universe may be a sheet of existence, a shimmering surface in an 11-dimensional expanse known as the bulk. And everything we see, every atom, every star, every dream made of neurons and electricity, is trapped on that sheet like patterns of light projected onto a curtain. The forces of nature are bound to this brain, unable to leave. unable to wander. But gravity, as soft and mysterious as a sigh drifting through a quiet room, is different. It slips between the seams of the universe, escaping our brain and spreading into the vastness of the bulk. Perhaps that is why it feels so weak. Why a small magnet on your refrigerator can overpower the full pull of the Earth. Perhaps gravity is not failing us. It is simply reaching elsewhere. As physicist Lisa Randall once said, "If extra dimensions exist, they must hide themselves well." Her words hang in the air like a lantern, dimly glowing in a long corridor. For decades, researchers have struggled to unify the forces of nature. Electromagnetism. The strong force and the weak force fit neatly into the mathematical tapestry of quantum fields. Gravity stands apart. Ancient, geometric, indifferent to the quantum rules. But the brain-world picture offers something almost startling in its elegance. A way for gravity to be part of the same story by allowing it to roam beyond the world we see. When I reflect on this theory, I often think of evenings spent watching the horizon fade into the soft haze of twilight. The sky looks like a boundary, yet we know the air extends far beyond what our eyes detect. The brain is like that. A boundary only to us, not to the deeper geometry of the universe. And the bulk is the unseen realm where gravity wanders like a traveler who refuses to stay within the borders others obey. Many physicists have tried to capture the spirit of this idea in words that feel both scientific and strangely intimate. Nima Arkani Hamed once remarked, "Sometimes a theory feels right because it explains not just what we know, but what we couldn't imagine before." His sentiment resonates with the brain concept, for it invites us to imagine dimensions not as abstractions, but as living spaces where forces breathe and move. To understand why gravity alone escapes into the bulk, we must imagine it not as a force tied to particles like photons or gluons, but as the curvature of space itself. If space has more directions than we see, then gravity naturally spreads into them. Its strength diluted the way a drop of ink fades when stirred into an ocean. This is why gravity feels fragile on our brain, why it whispers rather than shouts. It is not weak by nature, only weak by distribution. And so the question arises like the moon rising slowly over a quiet field. If the universe is a brain, what lies beyond it? Theories suggest other brands, parallel sheets of existence drifting in the bulk, each with its own laws of physics, its own story. Some theorists imagine these brains colliding like cosmic tides, triggering events as grand as the Big Bang. Others imagine them floating silently, never touching, separated by distances measured not in meters but in dimensions. Edward Witten once said, "M theory is a piece of music we have heard only a few notes of." And indeed, the brain world feels like a melody unfinished, haunting, almost familiar. It explains much, yet leaves room for wonder. This is the nature of all deep scientific ideas. They illuminate and obscure in the same breath. Moving gently from theory to intuition, we can imagine our brain not as a sterile mathematical sheet, but as something almost alive. A great cosmic skin stretching and breathing with the expansion of the universe. Stars spark across it like fireflies on a summer night. Galaxies swirl like luminous seeds caught in a slow drifting wind. And beneath it all, unseen, unfelt, the bulk extends into directions our minds cannot follow. In this picture, even the weakness of gravity becomes poetic. Imagine a voice trying to sing through walls. Not because it is quiet, but because it echoes in rooms hidden from us. That is gravity. A force whose song is shared with worlds we cannot see. Some experimentalists look for signs of this leaking. Tiny deviations in how gravity behaves at the smallest distances. None have been found yet. But the search continues. And as physicist Raman Sundram once said, absence of evidence is not evidence of absence, especially when the universe may be deeper than our tools allow us to measure. When I consider these ideas, I often ask myself what it means for us personally. If our universe is only one layer, one fabric in a greater cosmic loom, then our place in the cosmos becomes both smaller and grander at once. Smaller, because we are not the center of anything. Grander, because we belong to a structure vaster than any myth. The brain theory reminds us that knowledge is never finished, that reality may be infinitely layered. And there is a quiet lesson in that. A lesson about humility, curiosity, and the willingness to accept that the world is more mysterious than our senses reveal. We often imagine ourselves as beings who understand the universe, but perhaps we are beings learning to listen to it. As this reflection drifts toward its close like a calm tide withdrawing from the shore, I am moved by how these theories do not merely answer questions. They deepen them. The universe becomes a place not only of matter and equations, but of possibility. And in that possibility lies beauty. If the idea of our universe as a single brain in an 11-dimensional sea has touched something in your imagination, I invite you to share your thoughts. Let your curiosity ripple outward. If these explorations bring you calm, or spark wonder, or accompany you as you drift toward sleep, feel free to like and subscribe so we can continue these quiet journeys together. And as we end this moment of contemplation, one question remains floating like a lantern rising into the night. If gravity can wander beyond our world, what other truths might be waiting just beyond the edge of our perception? In the quiet expanse of theoretical physics, where imagination and mathematics hold hands across the dark canvas of the universe, there is a thought that refuses to fade. It whispers that the world we walk through each day may not be the full story. That space itself may contain hidden folds and tiny corridors curling beyond our perception. And that the fabric of reality is far richer than the human eye can ever claim. As we drift gently into this idea, the mind touches the first notion that captivated generations of physicists. The possibility that space possesses compactified dimensions. These dimensions are said to be wrapped so tightly that no microscope, not even those of tomorrow's dreams, could unravel them. They are smaller than atoms, smaller than the vibrations that give birth to light. So small that their presence becomes a silent influence rather than a visible shape. Edward Witten once remarked, "Hidden dimensions are not a fantasy, but a mathematical necessity." And in his voice one hears both conviction and wonder. If such curled spaces truly exist, they would quietly guide the vibrations of strings, deciding the identity of particles like a sculptor shaping clay with hands too delicate for us to witness. Yet even as we sit with that image, there arises another idea that stretches the imagination in a different direction. If some dimensions are impossibly small, could others be unexpectedly large? The ADD model dared to ask that question, proposing that extra dimensions might extend to the scale of a millimeter, vast by the standards of quantum physics. The thought alone feels like a gust of cold cosmic wind. For if such dimensions truly exist, gravity could wander into them freely, slipping through the cracks of space like a river flowing into hidden caverns. This possibility offers an answer to one of the oldest puzzles in modern physics: the faintness of gravity. Why is it so fragile, so delicate, so easily overpowered by the simplest magnet? In this model, gravity is not weak by nature. It is merely spread thin, stretching across dimensions that the other forces can never reach. Nima Arkani Hamed once said, "Gravity might seem weak only because we are not seeing the whole of where it lives." And perhaps there is a strange comfort in knowing that weakness can be nothing more than misperception. From there, the mind glides toward a more intricate possibility. One where extra dimensions do not merely exist, but are shaped and stretched in unusual ways. The Randall-Sundrum model imagines a universe where space is warped, curved like a soft ribbon drifting in water, its geometry bending the paths of forces and particles. In this warped landscape, an extra dimension could be present yet concealed, hidden not by size but by shape. Only gravity, ever the wanderer, seems capable of navigating these distortions, pooling in certain regions the way mist gathers in a quiet valley. Lisa Randall once wrote, "The universe may be more like a stage with unseen backstage hallways than a simple open room." And her words linger like a lantern held up to the dark. As we drift further into this thought, another possibility appears at the horizon of the mind. A world where every particle possesses a heavier echo. Universal extra dimensions suggest that matter is not singular, but layered, with each electron, each quark, each photon having a silent twin tucked into the folds of higher dimensional space. These twins, known as Kaluza Klein excitations, could be the shadows that dark matter has cast across the cosmos for billions of years. They may circle galaxies, hold their stars in place, and shape the cosmic web without ever revealing their faces. As Nobel laureate Frank Wilczek once observed, dark matter may be ordinary matter taking extraordinary paths through hidden dimensions. And the possibility is as humbling as it is beautiful. As each of these ideas settles gently into place, one sees how naturally they flow into each other, as if they were different verses of a single cosmic poem. Compact dimensions whisper of hidden structure. Large dimensions hint at gravity's secret journeys. Warped dimensions paint a world of curved shadows, and universal dimensions offer echoes of particles we have never met. Together, they form a tapestry of possibility, a story of a universe more layered than we ever dared to imagine. And here, drifting in this twilight between certainty and wonder, I find myself reflecting on what all of this means on a more human scale. If the universe hides dimensions beyond our senses, perhaps our lives also hold depths we seldom notice. Perhaps we too are multi-layered, carrying hidden rooms of memory, unanswered questions, and silent strengths waiting to reveal themselves. Just as physics teaches us to look beyond appearances, life invites us to search beneath the obvious, to listen to the quiet spaces where truth often lives. The lesson is simple but profound. That reality is never as small as it first appears. Our perceptions are narrow windows. Our senses are guides with limited reach. And our understanding is always in motion. Hidden dimensions remind us that the universe is patient, that it reveals itself one layer at a time, and that curiosity is the key that unlocks each door. There is humility in that realization, a gentle reminder that discovery is not a conquest, but a conversation, and so we drift back to the central question that has guided this journey, the soft thread woven through every idea. If gravity can wander through unseen corridors, if particles can carry echoes of themselves in hidden directions, if space can warp and coil and hide more than it shows, then what is the true shape of the universe we inhabit? And perhaps more importantly, how much of reality have we yet to perceive as we walk through our days under the quiet glow of the stars? Physics does not offer simple answers, but it offers wonder. And in that wonder we find a place to rest. A place where science becomes poetry, where questions become lanterns, and where the unknown is not a threat but a gentle invitation. As you breathe with these thoughts, let them drift and settle like stardust across the mind. Soft, patient, and endlessly open. For in the quiet spaces between what we know and what we hope to know, the universe waits, holding its unseen dimensions with the same calm certainty that dawn holds the promise of sunrise. Gravity has always been the quietest of the forces, yet somehow the one that pulls the deepest threads of the cosmos. It whispers rather than declares, bends instead of striking, shapes worlds with a patience that feels older than time itself. And tonight, as we drift through the soft darkness of thought, we turn our attention to a question that feels almost like listening for a heartbeat under the skin of reality. Does gravity behave differently when we look at it up close? Closer than a millimeter. So close that the ordinary rules begin to shimmer and blur. Physicists have spent decades building delicate instruments that feel more like musical tools than machines. Tiny balances that tremble under forces so subtle they can be drowned out by a passing footstep, or the breath of a distant elevator. They push gravity into spaces so small it is almost forced to reveal its secrets. And each time they test it, they are asking the same question in a new way. Does gravity fall off exactly, as Newton said? Or does it begin to fade faster than expected because it is quietly leaking into realms we cannot see? It is here that the idea of extra dimensions begins to hover at the edge of the conversation like a soft shadow. Not proven, not dismissed. As theoretical physicist Lisa Randall once said, if extra dimensions exist, they do not shout, they whisper. And these experiments are tuned to hear that whisper, to catch the moment when the pull of gravity thins just a little more than it should. But the story does not end with laboratory stillness. It stretches outward toward the blazing heart of particle accelerators. At the Large Hadron Collider, protons collide with energies so intense they momentarily mimic the conditions that shaped the newborn universe. In that chaos, scientists look for unusual absences rather than flashes. Missing energy that seems to slip away as if falling through a crack in the fabric of our world. Such missing energy would be more than a curiosity. It would be a signature, a soft footprint of a particle vanishing into a dimension just beyond our reach. Some theories even predict microscopic black holes forming for the briefest possible instant, evaporating before they can be seen, leaving behind patterns of particles like the fading outline of a spark in the night. As Stephen Hawking once reflected, the universe is not only stranger than we imagine, it is stranger than we can imagine. And these collisions test the edges of that strangeness. As we drift from the human scale to the cosmic scale, a gentle continuity emerges. For if extra dimensions shape the world of the very small, they must also guide the architecture of the very large. The way galaxies gather into clusters, the way voids widen between them, the way the invisible grip of dark matter sculpts the universe into a vast web like frost, stretching across a cosmic window. All of this may be touched by dimensions we cannot see. Cosmologists ask whether an unseen dimension could slightly shift the pull between galaxies, whether it could make stars orbit too fast in the outer arms of spirals, whether it could deepen the silence of cosmic voids. Some models hint that the mysterious acceleration of the universe itself might be influenced by a hidden geometry, a gentle outward pressure shaped not by energy alone but by the curvature of space extending beyond our three familiar directions. As astrophysicist Nima Arkani Hamed once said, "We may be living on a small corner of a much larger reality." And then there are the gravitational waves, ripples that move through the universe like the slow breath of creation. First detected in 2015, they have become one of our most intimate messengers from the depths of spacetime. If extra dimensions exist, these waves might lose a tiny portion of their strength as they travel, not because they weaken, but because part of their energy slips outward into another dimension like water seeping into hidden channels in the earth. If detectors ever notice such a deviation, it would be a revelation, a soft confirmation that we have been living alongside unseen realms all along. And so the experiments continue. Small instruments trembling in silence, giant accelerators roaring under the ground, observatories listening to waves older than the Earth itself, each of them searching in its own way for the same faint signature, the same hint that gravity is not confined to the world we see. For if gravity truly leaks, even a little, it means the boundaries of our reality are more porous than we imagined. To explore these possibilities is to navigate a territory where science and wonder meet, where equations trace the outlines of mysteries that feel almost spiritual in their depth, where the universe becomes not just a place but a poem we have only begun to read. It is a space where curiosity becomes a form of meditation, where every new discovery feels like turning a page in a book that has no ending. As we reflect on these questions, we find the edges of the known world becoming soft, dissolving into possibilities whose shapes we can feel even if we cannot yet see them. Gravity at a millimeter, particles vanishing at unimaginable energies, galaxies drifting under unseen influences, waves of space-time humming across the universe with secrets tucked inside their vibrations. All of them hinting that reality may be layered, overlapping, interwoven with dimensions that brush against our world like the passing of a quiet dream. In this slow drifting thought, in this gentle unraveling of what we believe to be true, we begin to sense that our universe may be both vaster and more intimate than we ever assumed. As physicist Brian Greene once said, Hidden dimensions may be the deepest secret that nature has kept from us. And we are just beginning to knock softly on the door of that secret. If gravity truly reaches beyond what we can touch, if particles slip through folds of space we cannot perceive, if waves lose their energy to realms our senses were never built to witness, then we are not just studying the universe. We are discovering where our reality ends and something else begins. And perhaps, in time, we will learn to listen more closely to the soft messages gravity has been sending since the first moment of creation. In the quiet reach of the cosmos, where stars breathe in slow centuries and space folds like soft fabric under the weight of time, a strange thought has begun to take root in the minds of physicists. What if the universe is not merely what we see, but the faint shadow of something deeper, something layered, something rising into dimensions that our senses cannot touch? And in that depth, what if the mysteries that trouble our equations are not mysteries at all, but reflections from hidden directions in space? Hashone number. When scientists speak of dark matter, they speak of an invisible hand guiding galaxies, a silent mass shaping the great cosmic spirals across billions of light years. They speak of its presence with humility because it refuses to be seen or touched, yet its fingerprint appears everywhere. But there is an idea whispered in the halls of theoretical physics, gentle yet revolutionary, that dark matter might not be matter at all, but the gravitational echo of a dimension just beyond our sight. The physicist Lisa Randall once said, "Sometimes the universe is more unimaginably strange than we can conceive." And perhaps it is in this strangeness that dark matter finds its home, not in particles dancing invisibly in our world, but in mass that exists in a parallel layer of space, whose gravity leaks into ours like light bleeding through a thin curtain. In moments of contemplation, one can imagine galaxies turning not because of missing matter, but because of the tug of something living beside us. Not here, not there, but in between. And as this thought softens the edges of the mind, another arises naturally. If dark matter can be a whisper from another dimension, could dark energy, the force stretching the universe apart, be the breath of geometry itself? Hashone number. Physicist Nima Arkani Hamed once remarked, "The universe is far simpler and far more beautiful when you allow additional dimensions." In that beauty, there is a possibility that dark energy is not a mysterious pressure from nowhere, but the gentle push of a higher dimensional space touching ours, shaping the way expansion unfolds. Imagine the universe as a sheet drifting on a larger sea, its ripples influenced by currents we cannot see. The acceleration we observe, the strange speeding up of galaxies, could be the natural result of our three-dimensional brain adjusting to the curvature of a greater world. One might pause here, letting the idea drift like smoke in a quiet room, to consider how elegantly this ties the puzzles together, how the invisible mass that holds the cosmos together and the invisible energy that pulls it apart could both emerge from the same hidden architecture. A deeper fabric pressing gently into our own. The physicist Edward Witten once wrote, "What we call physics is merely the shadow of the true structure of the universe." Shadows, reflections, glimmers of something larger. As we follow these thoughts, moving slowly as though drifting in a dream, another question rises from the horizon of imagination. If extra dimensions exist, then the landscape of space may not be the long, lonely stretch we once believed. Instead, it may be folded and curved, allowing hidden paths where distance collapses. Wormholes, those ancient doors of science fiction, might not be fantasies but natural tunnels carved into the higher geometry of the cosmos. Kip Thorne once said, "Wormholes are permitted by the laws of physics." A sentence both comforting and thrilling. If space bends in unseen directions, then two distant stars might be no farther apart than 2 points on a sheet that has been folded. A civilization, perhaps ours in some distant future, might learn to navigate these folds, stepping not through space, but around it. The idea feels like a sigh from the universe, an invitation to explore not by traveling fast but by understanding deeply. Yet science is not built on poetry alone, though poetry is often the lantern that reveals the outlines of truth. The possibility of dark matter and dark energy emerging from extra dimensions arises from equations as delicate as spider silk, from attempts to unify gravity with the quantum world. Gravity, the weakest yet the most universal of forces, behaves oddly in our equations. It refuses to fit neatly, unless one allows it to spread across dimensions beyond the ones we touch. Its weakness may be nothing more than dilution, its strength lost as it pours into spaces our senses cannot reach. And if gravity can slip across dimensions, then, of course, its effects, the clustering of galaxies, the bending of light, the stretch of space itself can also appear as mysteries in our limited view. Dark matter becomes a phantom only because its true form lives one layer deeper. Dark energy becomes a riddle only because its source lies in the shape of dimensions we cannot step into. As these ideas settle like dust in a sunbeam, the mind begins to sense something humbling. That perhaps we have been staring at the universe as one stares at a tapestry from too close, seeing threads where there should be patterns. Extra dimensions, if they exist, lift us back a few steps, revealing coherence where once there was confusion. Michio Kaku once reflected, "The universe is like a chess game, and we've only just learned how the pawns move." And indeed, as we learn of hidden dimensions, we begin to see that the board is larger than we knew, that some moves occur beyond our field of view. But there is also a gentler thought here, a meditative truth that settles deeper than physics. If the cosmos holds dimensions beyond our grasp, then reality itself is always more generous than our instruments suggest, more mysterious than our certainty allows. The unknown is not an emptiness, but a spaciousness, a reminder that wonder is a kind of knowledge, a way of listening to the universe even when it has not yet spoken clearly. Perhaps that is why the idea of wormholes, of dark matter as a neighboring world, of dark energy as the breath of geometry, feels strangely comforting rather than frightening. They suggest that the universe is not barren but layered, not silent but complex, not indifferent but elegantly constructed. And in this stillness, as one drifts through the thought that our cosmos might be only a surface on a deeper ocean, a quiet question begins to glow. If our familiar reality is shaped so profoundly by dimensions we cannot touch, then what else lies just beyond the veil, waiting for the day when our understanding expands enough to meet it? When we speak of reality, we often imagine it as something firm, stable, complete. Yet in the quiet hours of the night, when the mind softens and the world settles into its gentle breathing, a deeper possibility begins to shimmer beneath the surface. Perhaps what we see is not the whole of existence, but only the shadow cast by a far richer geometry. As the physicist Lisa Randall once reflected, reality may be shaped by dimensions we cannot perceive, woven like hidden threads through the tapestry of space. And in that thought lies the beginning of a profound unraveling. If extra dimensions truly exist, then everything familiar becomes a doorway to something deeper. Our three-dimensional world may not be the solid chamber we assume, but the surface of an immense and multi-layered realm. A shadow, drifting on the outer skin of a far greater body. This idea has long held the attention of physicists because our equations whisper that space is incomplete, that its fabric bends and curves more easily than it should. Stephen Hawking once said that the universe is not only stranger than we imagine, but stranger than we can imagine. And perhaps this strangeness is not chaos, but architecture. The thought that our world might be only a projection is unsettling at first. Yet it becomes strangely soothing when we imagine it in stillness, as if we are walking quietly across the floor of a great cathedral without realizing that countless chambers rise above us and plunge below. If these hidden dimensions do exist, then our senses are simply tuned to the thin plane where our lives unfold. But gravity, that soft, persistent pull, may wander freely into the unseen. And in that wandering it becomes weaker to us, diluted across a realm beyond our touch. The physicist Nima Arkani Hamed once remarked that gravity may be weak not because it is flawed, but because it is democratic, walking across more dimensions than any other force. From this possibility arises another. If space truly stretches beyond the familiar, might the cosmos contain countless separate realms, each formed by different arrangements of these hidden folds? This is the idea of the multiverse not as fantasy, but as a natural outcome of higher dimensional geometry. Just as shadows differ based on the angle of the light, universes may differ based on how these extra dimensions curl into themselves. Some may cradle stars made of unfamiliar matter. Others may never form galaxies at all. Ours is simply one note in a vast chord. Yet when confronted with these possibilities, our intuition falters. Human senses evolved for warmth, light, touch, the textures of our immediate world. We are creatures tuned for survival, not for perceiving the depth of space-time. Einstein himself reminded us that the most incomprehensible thing about the universe is that it is comprehensible at all. And here we face the limit of intuition. For when the mind tries to grasp dimensions beyond three, it feels as if the floor slips gently beneath our feet. Our thoughts reach outward but return with empty hands. Perhaps this failure is not a flaw, but a quiet invitation to humility. It is natural to wonder what these hidden dimensions would mean for our future. If we could touch even one of them, the frontier of our civilization would expand in ways difficult to imagine, yet soothing to contemplate in the soft rhythm of night. Some theories suggest that movement through higher dimensions could create shortcuts between distant points in space. A journey to a star 100 light-years away might become a gentle step across a fold in space-time, just as a traveler might pinch two corners of a map together to shorten the path. In such a world, the idea of faster-than-light travel would no longer violate the universe, but would simply make use of its deeper structure. Michio Kaku once described extra dimensions as the key to unlocking impossible dreams. And perhaps he was right. Energy, too, would transform. If space has hidden layers, then new forms of energy may lie curled within them. Not exotic, but natural aspects of a richer space-time. These energies might allow technologies that make today's achievements seem like early sketches. Silent machines drawing power from geometric symmetries. Spacecraft gliding through higher dimensional corridors. Communication that ripples across space-time like a whisper carried by a breeze. Theoretical physicist Juan Maldacena once suggested that space-time itself may be woven from quantum threads, connecting distant regions as if distance were an illusion. If communication could travel along those threads, messages might one day skip across vast cosmic expanses faster than light codes, moving through the unseen fabric between worlds. These visions may feel fantastical, yet they arise not from imagination alone but from equations that refuse to lie. Over and over, the mathematics bends toward the same conclusion. The universe has depth we cannot see. But what does that mean for us as individuals? For those who lie awake under quiet skies, feeling the faint pulse of something grander just beyond reach. It may mean that our lives are part of a story far larger than the one we can measure. That our thoughts and questions are not trivial, but the natural response of a mind touching the edge of hidden worlds. Yet no matter how beautiful the idea, science demands caution. Evidence must guide belief. And here lies the question that hums beneath every discussion of extra dimensions. Are we moving closer to the truth, or wandering deeper into mathematical dreamscapes? Some physicists argue that the lack of direct evidence hints that these dimensions may be nothing more than elegant illusions. Others maintain that we have only begun to build the tools needed to glimpse them. Edward Witten once said that if the theory is beautiful, it must be taken seriously. For beauty in physics is often a sign of truth. And string theory, with its requirement of hidden dimensions, remains one of the most beautiful frameworks ever written by human hands. As we drift further through these thoughts, it becomes clear that the question is not simply scientific. It is deeply human. To ask whether reality is complete is to ask where we ourselves belong within it. To wonder whether unseen dimensions exist is to wonder whether the universe holds more compassion than we believed. More mystery. More room for the fragile hope that we are part of something grand. We breathe, and the cosmos breathes with us. A shared rhythm flowing across the visible and the invisible. Perhaps the most comforting possibility is that the universe has always been larger than our perception. That the unseen layers are not hostile, but simply quiet, resting just beyond the boundary of our senses. If one day we learn to perceive them, humanity may step into a new era not of conquest, but of understanding, traveling gently through cosmic folds, listening to the silent geometry of creation, finding new ways to live in harmony with a universe more intricate than any dream. And so we return to the final question that echoes softly at the conclusion of this journey. Are we moving closer to the truth, guided by these mathematical whispers? Or are the extra dimensions nothing more than shadows cast by theories reaching beyond their grasp? The answer is not yet known. But in the quiet space between certainty and wonder, we find the beauty of exploration itself. For as long as questions remain, we continue to walk toward the unknown, guided by the gentle belief that reality, whatever its true shape, is waiting patiently for us to understand it.